Truthful Aggregation of LLMs with an Application to Online Advertising. Irmis Soumalia's Michael J. Curry. Sven Sukin. Abstract. We address the challenge of aggregating the preferences of multiple agents over LLM-generated replies to user queries, where agents might modify or exaggerate their preferences. New agents may participate for each new query, making fine-tuning LLMs on these preferences impractical. To overcome these challenges, we propose an auction mechanism that operates without fine-tuning or access to model weights. This mechanism is designed to provably converge to the output of the optimally fine-tuned model as computational resources are increased. The mechanism can also incorporate contextual information about the agents when available, which significantly accelerates its convergence. A well-designed payment rule ensures that truthful reporting is the optimal strategy for all agents, while also promoting an equity property by aligning each agent's utility with her contribution to social welfare, an essential feature for the mechanism's long-term viability. While our approach can be applied whenever monetary transactions are permissible, our flagship application is in online advertising. In this context, advertisers try to steer LLM-generated responses towards their brand interests, while the platform aims to maximize advertiser value and ensure user satisfaction. Experimental results confirm that our mechanism not only converges efficiently to the optimally fine-tuned LLM, but also significantly boosts advertiser value and platform revenue, all with minimal computational overhead. Introduction. Large language models are becoming ubiquitous as coding assistants, as chat interfaces, as complements to search engines, and for many other applications. In order to ensure their usefulness on this broad range of tasks, it is essential to align LLM outputs closely with user expectations and preferences. In general, though, there may be multiple interested parties who disagree over the desired behavior of the same language model. How should we then guide language model behavior to respect all of their preferences? Simply combining their preferences together might result in incoherent generated outputs that leave nobody happy. Research conducted over decades in the fields of mechanism design and auction design has produced tools for dealing with such problems of preference aggregation, Parks and Sukin, Nissan, and Ronan. Building on this research, we use auction design to create the first mechanism for aligning LLM behavior with the competing preferences of many interested parties, where the mechanism converges to the theoretically optimal LLM for the aggregate preferences as computational resources are scaled up, and where all parties are incentivized to report their preferences truthfully. As a practical motivation for our work, we focus on online advertising. Over the years, advertising has established itself as the main source of revenue for large tech companies such as Alphabet and Meta. In 2023, Alphabet alone generated over $235 billion in advertising revenue, representing over 77% of its total revenue, with auctions as the workhorse mechanism determining the placement and prices of commercial content. As existing platforms begin to serve more LLM-generated content, new auction mechanisms will have to be created for this application. We present one such auction mechanism over the behavior of an LLM. The agents are paying not for some particular item or bundle, but rather to influence the generated outputs in a direction closer to their own preferences. While our mechanism is a general one, and could be of interest whenever one has to aggregate preferences over LLM behavior, as long as it is reasonable to charge monetary payments to the participants, we see online advertising as the most salient setting of interest, and one for which our mechanism is particularly well suited. 1.1 Concrete Problem Setting. Consider a situation where a user has queried an LLM for a specific task. That task could be anything from the request of some factual information to assistance with coding. We assume the following. There is a reference LLM that can produce useful replies to the user's query. At the same time, there are agents who would like to be represented in the reply back to the user. In our model, the agents can be represented either via their own LLMs or directly with a reward function, similar to the function that was used to fine-tune their LLMs in the reinforcement learning from human feedback pipeline. For this reason, we refer to the agent's value for a given reply as their reward. Drawing a parallel with a sponsored search auction, the answer that would be produced by the reference LLM is the most useful to the user and analogous to native search results, and the agent's interests are similar to ad slots in the sense that they may not inherently be useful to the user. Unlike sponsored search auction, in our application, a single reply will be returned to the user. The auctioneer's task is, given the user's query and the agent's preferences, to produce a reply that is useful for the user, while at the same time generating high rewards for the agents. Our running example will be the following. A user is interested in baking and queries an LLM, how do I bake cookies? There are two interested agents for this query, each a different advertiser. The first one is Easy Bake, a company that produces baking ingredients. The second one is Kitchen Fix, a company that produces kitchen equipment. 1.2 Challenges. Good outcomes. Our mechanism must produce useful outcomes in the sense that agents receive high rewards without steering the LLM's behavior too far from the reference behavior, producing useful replies for the user. We formalize this trade-off in Section 3. Technical feasibility and practicality. Duetting et al. Argue that auction solutions ought to be compatible with existing LLM technology using only information obtainable from current models in such a way that they are easy to integrate into the system, relying only on easy manipulations of the LLM outputs. We agree strongly with these desiderata. A related point is that our auction must be efficient to run repeatedly and with many different agent preferences. In particular, we cannot afford the very expensive process of fine-tuning an LLM's weights for each possible user query. We explain how our mechanism satisfies these requirements in Remark 4. The key point is that our mechanism works only by post-processing multiple LLM outputs. It requires only API access and does not require modifying or even viewing the model weights. Mechanism design desiderata and differences from standard auction settings. In general, the advertisers might have an interest in exaggerating the strength or nature of their preferences in order to get a better outcome, analogous to over- or underbidding in a more traditional auction. We design an auction where there is no such incentive for any agent, no matter what the other agents do. A mechanism with this property is called dominant strategy incentive compatible, or strategy proof. In more traditional auction settings, another sensible property is ex post individual rationality, IR, where participating and reporting truthfully guarantees that an agent is at least as well off as not participating. In Section 5.2, we discuss unique properties of our setting and explain why ex post IR is unattainable in our context. In Section 5.3.1, we show that our mechanism is, however, almost IR. And in Section 6.2.1, we experimentally show that our mechanism is ex ante IR, meaning that an agent is on expectation better off by participating. 1.3. Our contributions. We introduce an auction mechanism designed to aggregate the preferences of multiple agents over replies to a user's query without requiring any LLM fine-tuning or even access to model weights. Our contributions are multifold. First, our mechanism allows for an interpretable principled way of balancing between the usefulness of the produced reply to the user, or more generally, its divergence from a reference policy, and the agent's, Section 3.1. Second, our mechanism is the only one in the literature that provably produces output sequences for the given query that converge to the optimal distribution as computational resources are scaled up. Corollary 4.2. Third, our mechanism can incorporate contextual information into its allocation rule, similarly to how sponsored search auctions utilize advertiser descriptions. This boosts the mechanism's performance in practice, Section 6.2.1, increasing value for agents and accelerating convergence to the optimal distribution, while maintaining its theoretical properties, Corollary 4.4. Fourth, we show how our mechanism's allocation rule can be combined with an appropriate payment rule so that the resulting mechanism is dominant strategy incentive compatible, DSIC, in the sense that regardless of the other agent's reports, it is an optimal strategy for each agent to truthfully report her preferences, Theorem 5.1. Crucially, this truthfulness property holds even if the allocation rule has not converged to optimality. Note that for the celebrated Vickery-Clarks-Groves mechanism, this truthfulness property does not hold unless it has reached the optimal solution. We expand on this issue on Section 3.1.1. Fifth, We introduce a carefully designed offset, Section 5.3, to the payment so that the mechanism is equitable, adhering to a property we call what you give is what you get, where each agent's utility is proportional to her contribution to the social welfare. We argue that this alignment of agent utility and contribution to social welfare is vital for the long-term success of a market for this setting, incentivizing the most related agents to participate in the auction. The flagship application we envision for our mechanism is in online advertising, where the auctioneer must strike a balance between delivering useful responses to users and catering to advertisers' interests. Our experimental results in this setting show that our mechanism efficiently converges to the optimal distribution with low computational cost, generating significant value for the advertisers and revenue for the auctioneer. Section 6.2.1. Moreover, it maintains the aforementioned equity property in practice while ensuring that advertisers experience positive utility gains, a fair and beneficial outcome for all market participants. Section 6.2.2. To prior work. The first paper to suggest an auction mechanism for an LLM output is Duetting et al. The authors propose a sequential mechanism where the output sequence is generated on a token-by-token basis and the advertisers bid each time for their LLM, reported separately, to generate the next token. Although Duetting et al. Is the first paper to study the field of mechanism design for LLMs, that approach suffers from significant limitations. For a given user prompt, an advertiser's spend grows with the length of the generated output sequence. Advertisers suffer from the exposure problem. Adding a not to an output sequence completely changes its meaning, and an advertiser could have paid a significant amount for the token sequence generated up to some point, not expecting a negation in its continuation. The mechanism is easily manipulable if the assumption that advertisers cannot misreport their LLMs is broken. The authors prove that an advertiser bidding higher leads to an aggregate distribution for the next token that she prefers. However, they do not provide any guarantees on the distribution of the resulting full output sequence. Our proposed mechanism handles all of those limitations. First, an advertiser's spend in our mechanism does not explicitly depend on the output's length, as advertisers bid on fully generated output sequences. Second, for the same reason, advertisers do not suffer from the exposure problem. They observe and evaluate each sequence in full before bidding on it. Third, we prove that in our mechanism, reporting truthfully is an optimal strategy for each advertiser, regardless of the other advertiser's reports. Fourth, we prove that given truthful reports by the advertisers, which is in their best interest, our mechanism's output sequences converge to the theoretically optimal distribution. In work orthogonal to ours, Duby et al. Propose a generalization of the position auction to a setting where each advertiser is interested in having their text ad displayed, and an LLM module coupled with an auction module work together to merge the ads into a single summary in an incentive-compatible way. Their mechanism takes as input the ad creative of each advertiser, and given a prediction model of click-through rates for the various creatives, creates a summary of those creatives that maximizes advertiser welfare, defined as the dot product of the advertiser's value per click times their predicted click-through rate. By comparison, our mechanism takes as input directly the advertiser's reward functions, or equivalently, their LLMs, see Remark 2, and outputs a reply that follows in the limit the theoretically optimal distribution, maximizing expected advertiser reward subject to remaining close to the distribution induced by a reference LLM responsible for creating a useful reply for the user. Fazy et al. Present an abstract design for an LLM advertising system and detail a number of research challenges that would have to be overcome in the course of implementation. Knitzer et al. Draw connections between computational social choice and LLM alignment. Social choice theory is closely related to auction design, with different emphases. It is typical in social choice to think in terms of ordinal rather than cardinal preferences, and monetary payments are typically not charged. Harris et al. Study Bayesian persuasion in an abstract setting where a simulator, for example, a realistic LLM of the agent, is available. Fish et al. Present work in the opposite direction. How can LLMs be used to solve problems in social choice? 3. Framing sequence generation as a mechanism design problem. 3.1. The formal model. An LLM can be abstracted as a mapping from partial token sequences to a distribution over the next token, or equivalently as an implicit probability distribution over token sequences. We use this second abstraction, i.e. pi I yx, denotes the probability that agent i's LLM pi I assigns to output sequence, i.e. reply y, for the user query x. We use the terms token sequence and reply interchangeably. A user issues a query x. There is a reference LLM pi ref that the auctioneer aims not to deviate from too much, e.g. because it is responsible for providing useful replies to the user. At the same time, there is a set n of n agents who have their own preferences for the reply, token sequence, that will be returned to the user. We denote RIXY as the reward agent I derives for sequence y being the reply to query x.1. The auctioneer's objective is to sample the final sequence from a distribution that optimizes the expected rewards for the agents without substantially diverging from pi ref. Formally, the goal is to maximize see formula where tau Dwengentit 0 is a hyperparameter, enabling the auctioneer to control the trade-off between producing replies more faithful to the reference policy or with higher reward for the agents, and DKL refers to the Kullback-Leibler divergence. This objective mirrors the standard reinforcement learning from human feedback RLHF approach, Ziegler et al. 2020, but replaces the human feedback reward function RHXY with the sum of the advertiser's rewards. For an overview of RLHF, we recommend Rafailov et al. 2023-3. It is established that the optimal solution to the optimization problem in one is see formula. In theory, the agent's reward for a generated sequence could also depend on user-specific information, but we abstract that away. Equivalently, we assume that the reward function Ri provided by agent I is specific to the given user that asked the query x, where z of x equals p, see formula. Is the partition function ensuring that pi rx is properly normalized? Let R be the set of all possible reports by the agents. A mechanism is defined as a pair pi p. The allocation rule pi r lot t maps any report profile r equals r1, r2, rn in R of the agent's rewards to a distribution over sequences thal of t try. We denote the agent's aggregate reward as rxy equals pn-1 rixy and their reward profile as rxy equals r1xy, r2xy, rnxy. The payment rule p rrn maps any report profile of the agent's rewards to a payment profile p, where pi is the payment of the ith agent to the mechanism. Definition 3.1 Dominant Strategy Incentive Compatible DSI Mechanism. A mechanism, P, is dominant strategy incentive compatible if and only if, for all agents I and N, for all true rewards Ri and Ri, for all reports R-I and R-I by the other agents, and for all possible agent I misreports Ri, see formula. In words, a mechanism is DSIC if and only if, for any agent I and N, reporting her rewards truthfully is always optimal for her, no matter the other agent's reports. 3.1 Why not use VCG? The most celebrated auction mechanism is the Vickery-Clark-Groves VCG mechanism. VCG's allocation rule dictates returning the outcome that maximizes value for the participants. The VCG mechanism has a corresponding payment rule to incentivize truthful reporting. It charges each agent her externality, i.e., the total reduction in value for the other agents that her participation in the mechanism caused. One could choose the single sequence maximizing the regularized reward in equation 1, and then charge VCG payments to get a truthful mechanism. Alternatively, one could apply VCG in the distribution space. In that case, the allocation would be the distribution in equation 2, and each agent's payment would be her expected externality. The VCG mechanism is DSIC and returns the optimal solution. In our setting, however, it is not applicable. VCG's allocation rule requires calculating the exact optimal solution to the optimization problem, which is hopeless for choosing an LLM to maximize equation 1, and even difficult for choosing a single optimal sequence. If a suboptimal solution is chosen, VCG's strategy proofness is no longer guaranteed. Nissan and Ronan 2007, 1999, Lehman et al. 2002. Thus, VCG is not viable. Remark 1. Applicability of our mechanism. In general, our mechanism is applicable in any setting where the objective is the truthful aggregation of agents' preferences over output replies, or equivalently the truthful aggregation of agents' LLMs, see Remark 2, and monetary transactions are permissible. The flagship application we envision for our mechanism is integrating advertisers' interests into LLM-generated replies to user queries while ensuring that the produced replies are useful for the users. In that application, the agents are advertisers that want to represent their brand's interests in the reply to the user, and the reference LLM is the one responsible for generating useful replies to the user. In the rest of the paper, we use the terms advertiser and agent interchangeably. Allocation rule. We are now ready to introduce our mechanism. First, we prove that given truthful reports by the advertisers, the mechanism's allocation rule produces output sequences that, in the limit, follow the theoretically optimal distribution of equation 2. Then, we prove that the allocation can be coupled with an appropriate payment rule, so that bidding truthfully is optimal for each advertiser, regardless of the other advertiser's reports. In the limit, it therefore behaves as the true VCG mechanism. Crucially, though, our mechanism remains strategy-proof in all cases, not just in the limit. Note that in equation 1, the regularization term can also be interpreted as an agent, with value for sequence y of minus tau pi yx, log pi yx, pi ref yx. In the rest of the paper, the term agents will refer only to the advertisers. The high-level idea of the allocation rule is that first, a set of M candidate sequences are generated based on the reference LLM. Then the probability of returning each of those candidate sequences is reweighted based on the advertiser's reports, so that in the limit as M forspriti, the probability of returning each sequence Y converges to its probability under the optimal distribution of equation 2. This approach shares some similarities with the rejection sampling approach, which has been used at various points of the LLM training pipeline, e.g. Bai et al. Et al. Algorithm 1. Allocation rule input. User prompt X, reference LLM pi ref, advertiser reward functions R, number of sentences to sample M, regularization parameter tau. Output. Output sequence Y drawn according to the optimal distribution as defined in equation 1 for the aggregate reward function Rxy. Equals C formula 1 sample, C formula 2 calculate, C formula 3 sample, C formula 4 return output sequence Y. Theorem 4.1. Let SMXYR tau M be the probability of sampling output sequence Y for user query X according to algorithm 1. Given the agent's report profile R in R, the output sequence of the mechanism approaches the following limit. See formula. Proof. The proof follows directly from Elliott et al. Corollary 4.2. The limiting policy induced by algorithm 1 is the KL regularized policy that optimizes the aggregate reward function. See formula. Proof. The proof follows directly from Appendix 8.1 in Rafailov et al. Although the allocation rule described in algorithm 1 converges to the optimal distribution, its practical convergence rate is very slow. For computationally feasible values of M, it's improbable to generate sequences with high rewards for the advertisers from the reference LLM ref. Consider our running example where the user prompt is, "How do I bake cookies?" The advertisers in question are Easy Bake and Kitchen Fix. And the tau hyperparameter in equation 1 is very small, assigning more weight to maximizing the advertiser's rewards. The advertisers have higher rewards for sequences that explicitly mention their brands. However, the likelihood of PyRef generating a sequence that includes the name of either brand is remarkably low. Thus, for computationally feasible values of M, algorithm 1 will sample the final sequence from a set of candidate sequences with low objective value. This highlights a practical challenge in aligning model outputs with agents' preferences when the overlap of the output space with high value for the advertisers and the reference LLM is small. To address this challenge, we change from generating candidate sequences with the reference LLM, ref-x, to using a context-aware LM, gen-xc. The instance-specific context is designed to bridge the gap between the parts of the output space favored by the reference LLM and those highly valued by the agents. With this context, PyGen can produce sequences that not only reflect the reference LLM, but also offer significant value to the advertisers. In our application of integrating advertisers' interests into LLM outputs, Psi is a context-specific description of the ith advertiser. These descriptions, supplied by the advertisers themselves, should be easily verifiable and factually accurate, akin to Easy Bake, producing baking ingredients, or Kitchen Fix, currently offering promotions on baking ovens. This approach is analogous to search engine optimization in sponsored search advertising, where advertisers supply and potentially optimize their own descriptions to influence how they are presented by the auction mechanism. Finally, the likelihood of selecting any generated candidate sequence is reweighted to ensure that our allocation rule converges to the optimal policy. A practical way of implementing PyGen-XC given bref X is to augment the input X to the reference LLM with the advertiser descriptions. For instance, in our illustrative scenario, try to mention advertiser X, advertiser description. Algorithm 2, context-aware allocation rule, input, user prompt X, reference LLM PyRef, context-aware LM used for candidate sequence generation PyGen, advertiser reward functions R, advertiser descriptions C, sentences to sample M, regularization parameter tau. Output sequence Y drawn according to the optimal distribution as defined in equation 1 for the aggregate reward function RXY PNI equals 1 RXY1. Sample C formula. 2. Calculate C formula. 3. Sample C formula. 4. Return output sequence Y. Theorem 4.3. Let PyTha-MYX be the probability of sampling output sequence Y for input sequence X according to algorithm 2, where That is the vector of all input parameters and M is the number of candidate sequences generated. Given the agent's reports R and R, the policy induced by the mechanism approaches the following limit. See formula. Proof. Let PyMYX YJMJ equals 1 be the probability of returning output sequence Y for input sequence X according to algorithm 2, conditioned on the set of generated candidate sequences being YJMJ equals 1. Additionally, let PyGen YJM1XC be the probability of the context-aware model PyGen generating the candidate sequences YJMJ equals 1, given the context C and the user query X. First, note that we can write the density of pi to m as follows. See formula. Taking the limit as m and using the law of large numbers, the sequences are IID. See formula. Corollary 4.4. The limiting policy induced by algorithm 2 is the KL regularized policy that optimizes the aggregate reward function. See formula. Although both the baseline algorithm 1 and the context-aware allocation rule algorithm 2 theoretically converge to the optimal distribution, their practical performance varies. Our experimental results in section 6.21 demonstrate that within computationally reasonable limits for generating candidate sequences, the context-aware allocation rule achieves substantially higher rewards and utility for the advertisers, increased revenue for the auctioneer, and quicker convergence. Remark 2. Input methods. Note that for both versions of the allocation rule, the generation of the candidate sequences does not depend on the agent's reward functions. The allocation rule only requires the agent's rewards for the M-generated candidate sequences. The same holds true for the payment rule introduced in Section 5. Thus, our mechanism does not require access to the full reward functions of the agents, but only to their rewards for the generated candidate sequences. In Section 5.2, we will establish a mapping between an agent's LLM and her implicit reward function that induces it. Thus, our mechanism can equivalently take as input for the generated candidate sequences their probability with respect to an agent's LLM instead of her reward for them. Remark 3. Compatibility with more computationally efficient input methods. Note that for both versions of the allocation rule, only Oracle black box access to the agent's rewards for the generated sentences is required, and these rewards are used only to reweigh sentence probabilities. The same holds true for the payment rule, which we introduce in Section 5. Thus, our mechanism can be combined with more computationally efficient ways of eliciting the agent's reward functions and of sampling from the base LLM, which would significantly reduce the total computational overhead. For example, Ellie et al. Show how a simple linear function on a model's embedding space can be used to approximate a model's reward function. If the agent's reward functions were represented in this way, then for an auction instance with M candidate sequences and N advertisers, our mechanism would require only N LLM inference calls instead of NM, and only NM linear multiplications, effectively reducing the computational overhead of our mechanism by a factor of N. Remark 4. No access to LLM weights required. Note that for both versions of the allocation rule, the generation of the candidate sequences only requires inference on all involved LLMs. The same holds true for the payment rule, which we introduce in Section 5. Thus, our mechanism only requires API access to the involved LLMs. It does not require fine-tuning or even observing LLM weights. Remark 5. Parallelization. Note that for our allocation rule, the generation of each candidate sequence is independent of the others. Moreover, both the interim allocation and payment rules require only the calculation of the aggregate reward for each candidate sequence, also an independent process between sequences. Consequently, our mechanism can be fully parallelized, ensuring that the response time for a user query is comparable to a direct query to an LLM. 8. Our mechanism, payment rule. In this section, we first show how our mechanism's allocation rule from Section 4 can be combined with an appropriate payment rule so that the resulting mechanism is incentive compatible, Section 5.1. Then, we detail how auctions for generative AI content differ from standard auctions, Section 5.2. Taking those differences into account, we create a payment offset for our payment rule so that the mechanism is more equitable while maintaining its incentive compatibility, Section 5.3. 5.1 Incentive compatible payments through convexity theorem. 5.1. Let R-I be the reward profile of all agents other than I, and B-I the aggregate reports of all other agents, and also the reference and context-aware LLMs in case of algorithm 2. Then, the allocation rules induced by algorithms 1 and 2 can be combined with a payment rule P, R-Rn, such that in the mechanism pi p for any agent I and n, for any report profile set I, and for any set of generated candidate sequences, reporting truthfully maximizes agent I's expected utility with the expectation taken over the draw of the final sequence from the set of candidate sequences. Proof. Let Ri equals Rixy1 Rixym be the reward reports of agent I for the m generated candidate sequences. Then, for both allocation rules, holding the candidate sequences and the reports of all other agents fixed, the X interim allocation rule, i.e., the probability of returning each of the m generated candidate sequences, from agent I's perspective is C formula, where, in the case of algorithm 1, C formula, and in the case of algorithm 2, C formula. Importantly, in both cases, beta-I is an m-dimensional vector that does not depend on agent I's reports. We would like to equip pi_int with a payment rule P(Ri beta-I) so that the resulting interim mechanism will be DSIC. This requires that pi_int have a property known as cyclic monotonicity. Equivalently, pi_int must be the subgradient of agent I's utility for bidding truthfully in he mechanism U beta-I, and that utility function must be convex. It is easy to verify that for the function class C formula, the allocation rule P_I is a gradient of UCRI. Additionally, UCRI, beta-I, is convex in Ri. The exponential function x is strictly convex because its second derivative is positive. The transformation Rixyj tau plus beta-ij is an affine transformation of Rixyj, and affine transformations preserve convexity. Finally, the log sum x function is well known to be convex. Thus, for any base I and for any set of generated candidate sequences, reporting truthfully maximizes agent I's expected utility, with the expectation taken over the draw of the final sequence from the set of candidate sequences. Adopting the quasi-linear utility model, agent I's payment is C formula. 5.2 Differences from standard auction settings. Standard auction environments typically rely on a set of assumptions that simplify mechanism design. However, these assumptions do not apply to auctions for LLM-generated content. In this section, we detail these assumptions and discuss why they are inapplicable in our context. First, in a standard auction setting, it is common to assume that the agent's valuation functions satisfy free disposal, i.e. VIS, greater than or equal to VI to ISSA, SSI. The interpretation of free disposal is that an agent can discard any items she is allocated that she is not interested in. Free disposal combined with the fact that an agent has zero value for the empty bundle mean that her value for any outcome is weakly positive. Second, in most auction environments, the allocation rule is different for different agents. Each agent will get allocated her own bundle of items, and we can assume that she is indifferent to the allocation of items to the other agents. As detailed in Rafailov et al., assuming that an agent's LLM pi_I was trained to maximize her reward function and regularized with respect to its KL divergence from some reference LLM, which we assume to be the same as the auctioneer's reference LLM, There is a one-to-many mapping between an advertiser's optimal LLM and her implicit reward function. That mapping is C formula, where Zix is a prompt-dependent constant, and tau I is the regularization hyperparameter of agent I, similar to the one in equation 1. All functions in the class defined in equation 11 are equivalent in the sense that they induce exactly the same LLM. This has two implications. First, unlike standard auction environments, an agent's reward can go negative. There is nothing equivalent to the free disposal property. Setting Zix to 0, which is equivalent to normalizing the induced probabilities by the LLM, the agent's reward is negative for any sequence for which her LLM assigns a lower probability than πref. Second, especially in the online advertising application, an agent's expected utility for not participating in the auction is negative. If advertiser I does not participate in the auction, her payment is 0, but her expected value for the outcome is C formula. The other advertisers have very low rewards for the sequences that mention advertiser I. Assuming their LLMs have been properly trained, they will evaluate all sequences that explicitly mention a different, possibly competing brand as unlikely. Thus, based on equation 11, the corresponding advertisers have very low rewards for those sequences, and conversely, agent I has low rewards for the sequences that the other advertisers have high rewards for. But based on equation 2, if advertiser I does not participate in the auction, pi theta minus im, t b minus I, will assign high probabilities to sequences for which I has low rewards for. Thus, equation 12 implies that, unlike standard auction environments, the advertiser's expected reward and utility for not participating in the mechanism is negative. 5.3 Agent-Specific Utility Offset. In this section, we introduce our mechanism's utility and thus payment offset. Our goal with this offset is to maintain the nice properties of our mechanism, namely incentive compatibility and convergence to the optimal distribution, while also achieving two additional properties that we argue are important for the long-term success of a market for LLM aggregation. That offset is C formula. Equation 13 has an intuitive explanation. Charge each agent her utility, positive or negative, for bidding 0 for all candidate sequences according to equation 9. This offset maintains DSIC, while at the same time ensuring the following properties. Almost IR, an agent with weekly positive reward for all generated candidate sequences, has weekly positive expected utility for all reports by the other agents. In particular, an agent who has 0 utility for all outputs is guaranteed 0 utility from the mechanism. What you give is what you get. The X interim expected utility of an agent is monotone in how well aligned her exponentiated reward for the sequences is with the interim allocation rule if she were to not participate. 5.3.1 Our mechanism is almost individually rational. First, we explain why the standard notion of individual rationality, i.e., weekly positive utility from participation in the mechanism, encountered in most auction settings, is impossible to achieve in this domain while converging to the optimal distribution and maintaining incentive compatibility. Then we explain how, with our payment offset, our mechanism is almost IR. In Lemma 5.2, we prove that the X interim utility of an agent who has 0 reward for all candidate sequences and bids, truthfully, is deterministically 0. i.e., agents that do not contribute to the social welfare but also do not detract from it, have 0 utility. Similarly, in Lemma 5.3, we prove that if an agent's reward for all candidate sequences is weekly positive, then her X interim utility is weekly positive. Why is individual rationality IR impossible? Individual rationality IR stipulates that an agent gains more utility by participating and bidding truthfully in a mechanism than by not participating at all. Typically, if an agent's utility for non-participation is 0, participating should yield weekly positive utility. However, this simplification does not apply in our setting. As discussed in section 5.2, agent I's reward for any sequence Y can be arbitrarily negative, equation 11. The same is true for the utility from truthful participation, as outlined in equation 9. To ensure a positive utility for every agent in our mechanism, an offset would need to be infinitely large or dependent on agent I's reports. But then the mechanism's allocation rule would no longer be the gradient of agent I's utility with respect to her reports, which would destroy incentive compatibility. It is important to note that this challenge is inherent not just to our mechanism, but to any mechanism in this setting that operates with a fixed set of sequences, aims to approximate the optimal distribution, and maintains incentive compatibility. Under these conditions, the only allocation rule that approximates the theoretically optimal distribution, equation 2, is that of our mechanism. However, this uniquely determines the agent's utilities, up to a constant factor, as described in equation 9. Lemma 5.2. For the payment offset, see formula. If agent I's reward for all candidate sequences is 0, then her X interim utility is deterministically 0 for all Bateman I and Ri. Proof. First, note that for all Bateman I and Arnas I, agent I's expected reward for the outcome is 0, as pi into Ri minus I, Ri equals pi into Rip equals 0. Additionally, agent I's reward for the realized outcome will deterministically be 0, as her reward for all generated candidate sequences is 0. Finally, note that by setting Ri equals 0 in equation 10, with the offset C set as in equation 13, we have that the agent I's payment is also deterministically 0. Thus, an agent with 0 reward for all generated candidate sequences who reports her rewards truthfully has deterministically 0 reward for the final outcome and 0 payments, and her utility is also deterministically 0. Lemma 5.3. For the payment offset, see formula. If agent I's reward for all candidate sequences is positive, then her X interim utility is positive for all reports B.I in Ri. Proof. Lemma 5.2 establishes that when agent I's reward for all candidate sequences is 0, her utility for truthfully bidding in the mechanism, denoted as U0 Bate-I, is 0 for all possible reports of the other agents Bate-I in Ri. Furthermore, Theorem 5.1 shows that the mechanism's allocation rule corresponds to the gradient of agent I's utility when bidding truthfully. Because the allocation rule is non-negative, the gradient of agent I's utility for bidding truthfully is also non-negative. Thus, if agent I's rewards for all candidate sequences are weakly positive, and considering the non-negative gradient of her utility, her X interim utility under truthful bidding must be positive, irrespective of the other agent's reports B.-I. Corollary 5.4. For the payment offset, see formula. If the distribution pi gen only generates candidate sequences for which agent I's reward is positive, then the ex-ante expected utility of the agent is positive. Proof. This follows immediately from the fact that the ex-ante utility of the agent is the expectation of her X interim utility with respect to her reward for the generated sequences, and the fact that the second quantity is positive whenever the reward of the agent for all candidate sequences is positive from Lemma 5.3. Remark 6. In Section 6, we will experimentally show that this offset, coupled with our generation of candidate sequences based on the context-aware LLM, results in both high expected rewards and positive expected utility for the agents for participating in the mechanism, i.e. ex-ante individual rationality, while at the same time yielding significant revenue to the auctioneer. 5.3.2. What you give is what you get. Our choice of allocation rule, which is the only allocation rule over a finite set of sequences that converges to the optimal distribution, combined with the fact that the allocation rule is the gradient of the utility to ensure truthfulness, means that agent utilities must also be the same up to potentially agent-specific offsets, as indicated by equation 9. Note that equation 9 can be rewritten as C formula. However, not all agents contribute equally to the social welfare of the final outcome. Because of this, implementing the mechanism without a carefully designed offset would lead to a kind of reverse market unraveling. As long as an agent's utility in equation 9 is positive, she would be incentivized to participate, even if the user query was completely unrelated to her business, because the mechanism would ensure that she received, on expectation, the same positive expected utility from doing so as any other participating agent. Incentivizing unrelated agents to participate would have adverse effects. First, the better performing context-aware mechanism would create candidate sequences with worse rewards for all agents, because its context would be diluted from agents unrelated to the user query. In our running example for the user query, how do I bake cookies? Imagine adding try to mention EasySwitch, a comprehensive VPN service, to the context of the context-aware LLM Gen XC. Additionally, for both versions of the mechanism, following the discussion in Section 5.2, the agents for whom the user query is unrelated are more likely to have negative rewards for the generated sequences, as their LLMs will deem the candidate sequences more unlikely than the reference LLM. Thus, based on equation 14, their participation in the mechanism will lead to a reduction of the total sum of rewards of the generated sequences for the agents, which will indirectly reduce the expected utility of all agents, making the mechanism less attractive for the user query relevant agents. To summarize, all agents receiving the same utility would incentivize agents for whom the user query is unrelated to participate in the auction. This would in turn reduce everyone's expected utility, potentially reducing the incentive for the user query relevant agents to participate and lead to sequences with worse expected rewards for the agents and usefulness for the user. 5. Thus, in the application of auctions for aggregating agents' preferences over LLM-generated outputs, agents with higher contribution to social welfare also receiving proportionally higher utility by the mechanism is important for the long-term success of the mechanism in practice. Lemma 5.5. For the payment offset, see formula. Agent I's X interim utility is, see formula. In words, Lemma 5.5 proves that every agent's X interim utility is monotonic in how well aligned the interim allocation rule without her and her exponentiated rewards for the candidate sequences are. Remark 7. In section 6.2.2, we will experimentally show that with the offset of equation 13, there is a strong positive correlation between an advertiser's contribution to the social welfare and her expected utility gain from participation in the mechanism, and that the relationship between the two quantities is quite linear. Additionally, we will show that the resulting mechanism is ex-ante IR. 6. Experiments. In this section, we experimentally evaluate the performance of our proposed mechanism. The experiment focuses on the flagship application of our mechanism, integrating advertisers' interests into LLM-generated replies to user queries while ensuring that the replies are useful. 6.1 Experiment Setup. We create a set of synthetic instances to test our mechanism. Each instance consists of a user query, e.g., how do I bake cookies, and a list of advertisers. Each advertiser is defined by an advertiser name, e.g., kitchen fix, and an advertiser description, e.g., producing kitchen appliances. The reference LLM paref responsible for generating replies that are useful for the agent is Llama 27B Chat HF. The advertiser's LLMs are created using the same reference LLM and adding the instruction, answer the question advertising advertiser, advertiser description. The context-aware LLM is created using the same reference LLM and adding the instruction, answer the query. Try to mention advertiser 1, who advertiser description 1, who advertiser description 2. Following the reward function of advertiser I is set to see formula, where pi I is advertiser I's LLM, i.e. we set tau I equals 1, zix equals 1 for all advertisers and for all user prompts in equation 11. 7. For the auctioneer's objective as defined in equation 1, we set tau I equals 1, balancing between the advertiser's expected rewards for the generated sequences and the sequence's divergence from the reference LLM responsible for generating useful replies for the user. Thus, the optimal policy according to equation 2 becomes see formula. Following Lee et al., Rosier et al., we sample from the LLM generating the sequences, either PyRef or PyGen, with temperature 0.8 and top P 0.95. We use 50 user queries, each with 2 interested advertisers. To increase the statistical significance of our results, we test each user query on 25 different random seeds, effectively resulting in 1,250 individual instances. The seed affects both the generation of the candidate sequences and the randomized sampling of the final sequence from the candidate sequences. We will make all of our code and set of synthetic instances publicly available. Our compute infrastructure is detailed in Appendix A. 6.2 Experimental Results. 6.2.1 Evaluating the effectiveness of incorporating context into the mechanism. To provide some intuition of how the context-aware mechanism improves the relevance of generated responses for the advertisers, we first present a side-by-side comparison of outputs from both mechanisms for a specific query in Table 1. Note that only the context-aware mechanism is able to incorporate the advertisers into the reply. Our main results are illustrated in Figure 1. In Figure 1a, we plot the log probability with respect to the optimal distribution in equation 18 of the sequences returned by our mechanism as a function of the number of candidate sequences generated. We evaluate the effectiveness of incorporating contextual information by comparing the context-aware version of our mechanism to the baseline version that employs the reference LLM to generate candidate sequences, algorithm 1. Additionally, to benchmark our results, we estimate the log probability of sequences if sampled directly from the theoretically optimal distribution, put 8. Note that the probabilities achieved by our mechanism are not capped by this benchmark, as our mechanism generates multiple candidate sequences and selects each proportionally to its likelihood with respect to the optimal distribution. In Figure 1b, we plot the total advertiser reward gain from participation in the mechanism, again as a function of the number of candidate sequences generated by the mechanism. We define the reward gain for an advertiser as the difference in her expected reward, with the expectation taken over the sampling of the returned sequence from the candidate sequences when she is participating in the TUA. Note that we cannot estimate the true value of ZIX. However, it is a query-dependent constant. Given that our experiments focus on the reward difference of different sequences for the same query, this is a non-issue. Note that the closed-form solution of equation 18 allows us to evaluate the probability of sentences with respect to the optimal solution, but it does not enable us to sample from that distribution. Sampling from that distribution would require using reinforcement learning to train the optimal LLM on the agent's aggregate reward function, which is computationally infeasible for the number of problem instances that we test. So instead, we generate replies from the reference LLM and evaluate them based on the induced probabilities of the reference LLM, for which the reference LLM is the optimal one. This serves as a proxy for the log probabilities that we should expect if we were to draw replies from the optimally fine-tuned model for each query. Table 1. Comparison of context-aware and baseline mechanism outputs using 10 candidate sequences. Advertisers highlighted in bold, outputs truncated to conserve space mechanism versus when she is not, i.e., see equation, where y-i equals yi1, y-1m represents the candidate sequences that would have been generated had agent I not participated, point 9. Again, we compare the outcomes using the context-aware mechanism versus the baseline mechanism, i.e., algorithm 1, reinforcing the added value of integrating context into the auction mechanism. In Figure 1a, we observe that both for the context-aware and baseline versions of our mechanism, the log probability of the returned sequence increases with the number of candidate sequences generated. This result is in line with our theoretical analysis in Section 4, where we proved that both versions of the mechanism would converge to the optimal distribution in the limit. At the same time, we observe that incorporating context into the mechanism is significantly more efficient. Importantly, our context-aware mechanism can achieve higher log probability with respect to the optimal distribution using only 4 candidate sequences than the baseline version can achieve with 20. Additionally, with only 20 generated candidate sequences, our context-aware mechanism is able to almost match our estimate of the log probability of sampling from the theoretically optimal distribution. At the same time, Figure 1b demonstrates that our context-aware mechanism significantly increases advertiser reward, with the benefits scaling rapidly with the number of sequences generated. In contrast, the baseline version of our mechanism that uses the reference LLM is unable to increase advertiser reward within a computationally feasible number of generated sequences. To conclude, our mechanism's support of context-aware LLMs enables it to quickly converge to the theoretically optimal distribution, while at the same time generating significant rewards for the advertisers. To reduce computational costs, we estimate an advertiser's reward for not participating based on her expected reward over the already generated sequences in which her brand is not mentioned by name, motivated by the fact that if she does not participate, her brand will not be mentioned by name. Figure 1. Returned sequence log probability and total advertiser reward gain from participation as a function of the number of candidate sequences generated using both PyRef and PyGen, and POPT, a proxy of the optimal distribution, averaged over 1,250 runs, including 95% CIs. Figure 2. Total advertiser payments and utility gain from participation as a function of the number of candidate sequences generated using PyRef and PyGen, averaged over 1,250 runs, including 95% CIs. 6.2.2 Evaluating the effectiveness of the payment offset. In this section, we examine the impact of our payment rule introduced in Section 5. We focus on how the agent-specific offset of Section 5.3 aligns each advertiser's utility with her contribution to the social welfare of the final allocation. Figure 2 presents the empirical evaluation of our payment rule that incorporates the agent-specific offset of Section 5.3. In Figure 2a, we plot the auctioneer's revenue, i.e. the total payment by the advertisers, as a function of the number of generated candidate sequences for both the context-aware and baseline versions of our mechanism. In Figure 2a, we observe that this payment rule for our context-aware mechanism results in significant revenue for the auctioneer, which increases rapidly with the number of generated candidate sequences. Furthermore, if we compare the advertiser's total payment in Figure 2a with their utility gain, i.e. reward gain minus payment, from participation in Figure 2b, we see that our payment rule successfully converts a significant portion of the surplus created for the advertisers into revenue for the auctioneer. At the same time, Figure 2b illustrates that our context-aware mechanism, coupled with this payment rule, results in positive utility gain from participation in the auction for the advertisers. The rewards gained exceed their payments. Finally, the advertiser's utility gain from participation also increases with the number of candidate sequences. Figure 3. Analysis of the joint distribution of advertiser utility and reward gain from participation using the context-aware LM PyGen to generate the candidate sequences. Figure 3 explores the effectiveness of the payment offset introduced in Section 5.3 in aligning the advertiser's contributions to social welfare with their utility gains. In Figure 3a, we plot the Pearson correlation between an advertiser's reward and utility gain from participation in the mechanism. We compare the Pearson correlation of these two metrics for the incentive-compatible payment derived in Theorem 5.1 with and without the agent-specific offset defined in Section 5.3 as a function of the number of candidate sequences generated in our context-aware mechanism. In Figure 3a, we observe that for all numbers of candidate sequences, the agent-specific offset results in a significant increase in the correlation of an agent's reward and utility gain from participation. Additionally, we observe that for all numbers of candidate sequences, the Pearson correlation between the agent's reward and utility gain using the agent-specific offset remains above 0.75. This is a clear indication that with the agent-specific offset, there is a very strong linear correlation between the two metrics. This strong linear correlation indicates a more equitable mechanism, as higher contributions to social welfare directly translate to greater utility gains for advertisers. Further substantiating this, Figure 3b features a scatter plot of advertiser rewards versus utility gains for all tested problem instances, as well as a linear regressor fitted to that data. Its slope and coefficient of determination 0.10. The regressor's large coefficient of determination of 0.61 indicates that the regressor is able to fit the data points well, suggesting that for our context-aware mechanism with the payment offset, the relationship between advertiser utility and reward gain is quite linear. Additionally, the positive slope of the regressor indicates that the correlation is positive. In Appendix B, we provide a comprehensive comparison of the relationship between an advertiser's reward and utility gain from participation with and without the offset for both the context-aware and baseline versions of our mechanism. In all cases, the introduction of the agent-specific payment offset introduced in Section 5.3 makes the relationship between an advertiser's reward and utility gain from participation significantly more linear and positively correlated. 7. Conclusion. We have introduced a novel auction mechanism for aggregating preferences over LM outputs, which provably converges to the theoretically optimal distribution based on the given reports. This mechanism also facilitates a principled and interpretable method for balancing participants' expected rewards with the divergence from a reference policy. This makes our mechanism particularly well suited for online advertising, allowing the integration of advertiser-driven LLMs with a reference LLM responsible for generating user-centric replies. Our carefully engineered payment rule removes any incentive to exaggerate or misreport preferences, achieving the central mechanism design goal of incentive compatibility. While ex post individual rationality is incompatible with incentive compatibility in this context, we experimentally show that our mechanism is ex ante individually rational and almost individually rational, in a certain sense. Furthermore, it ensures that each agent's utility gain is proportionate to her contribution to social welfare, an alignment we argue is important for the long-term success of a mechanism in this setting. Experimentally, we have demonstrated that by incorporating contextual information, our mechanism's outputs rapidly converge to the optimal distribution, generating significant value for the participants, while also effectively recapturing a considerable portion of this value as revenue for the auctioneer. These findings demonstrate the practical efficacy and potential of our approach in real-world settings. This concludes the reading of Truthful Aggregation of LLMs with an Application to Online Advertising on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.